Hello everyone, for SCUDEM 10 2025, we chose problem A. It is raining space dust. We are team 1007 and our coach is Dr. Jorge Mauricio Ruiz. My name is Jhon Acosta and I'm from the National University of Colombia.
Hi, I'm Juan Nicolas Mendoza Roncancio, and I'm a math student at Universidad Nacional de Colombia.
Hi, I am Tomas Rodriguez. I am a computer science student at Universidad Nacional de Colombia. Okay, so I'll start with a bit of context about the problem. Here we're looking at cosmic dust, which are tiny solid particles that enter a planet's atmosphere with a wide range of sizes and speeds. And this matters because dust participates in a lot of processes. That statement gave us two problems. The first one was the direct problem, and the question is like, if a particle with a given size and velocity enters the atmosphere, what happens to it on the way down? More concretely, we want to know how its survival and final state depend on radius and entry speed. Does it reach the ground intact, does it melt, or does it completely vaporize? And the second problem was the inverse one. So suppose we have the layer of soil or ice where we can measure the size distribution of dust grains that actually reach the ground. Can we work backwards and reconstruct what the incoming distribution was at the top of the atmosphere? Now for the assumptions. The first group is about the geometry. We treat each dust grain as a spherical homogeneous particle with constant density. We ignore fragmentation and rotation during entry, so all the mass stays in a single body. About the entry direction, we assume a vertical trajectory. We don't model lateral motion or different drag. Gravity is taken as constant. This let us focus on the competition between drag, heating, and radiation without solving a full 3D trajectory problem. For the atmosphere, we fix the air temperature at about 240 Kelvin, representing a mid-atmosphere layer, and we ignore short-time variations such as sudden winds. We also consider the atmosphere as an ideal gas.
For the direct problem, this is our mathematical model. Here we present the system of three differential equations that describe the fall of a cosmic dust particle through Earth's atmosphere. The first equation represents how height changes with time. It's simple to tell us that the higher the velocity, the faster the particle descends. The second equation comes from Newton's second law, balancing gravity, which pulls the particle down, and drag, which opposes its motion. The third equation is the energy balance, describing how the particle gains heat from air friction and loses heat through radiation. Together, these three equations define the direct problem, predicting what happens to the particle of given size and velocity as it enters the atmosphere. To solve the system, we first need to describe the atmosphere. We model it is an isothermal fluid in hydrostatic equilibrium, which means that as altitude increases, pressure and density both decrease. On the right, we can see how air density decays exponentially with height. This simple assumption gives us a continuous function for air density that's easy to use in the equations, avoiding the need to divide the atmosphere into layers. Now, let's look at the forces and fluxes acting on the particle. When the dust grain enters the atmosphere at very high velocity, the air no longer behaves like a smooth fluid. Instead, it collides constantly with the particle. These collisions produce two key effects: a drag force that resists the motion and a strong heating flux that transfers energy to the surface. The expression shows here giving us the magnitude of the drag depending on air density, velocity, and the frontal area of the particle. Applying Newton's second law, the sum of all forces equal masses times acceleration. The downward force is gravity, and the upward force is drag. Subtracting them gives the equation of motion, which governs how the velocity changes during the fall. The small diagrams on the right shows this balance visually. Gravity acts downward while drag acts upward, opposing the motion. The second part of the motion is purely kinematic. The first equation of our system simply relates the rate of change of height to the downward velocity. It's a straightforward link between how fast the particle moves and how quickly it descends through the atmosphere. The third equation in our system deals with energy. It shows the balance between heating by air friction and cooling by radiation. The first term on the left is called with air density and the cube of velocity, representing how kinetic energy from the air transfers to the particle. The second term on the right represents radiation losses, which is scaled with temperature to the fourth power. If heating dominates, the internal energy increases, and the particle may melt or vaporize. If cooling dominates, it remains intact. Here we separate the energy flow into input and output components. The incoming energy, Q in, comes from the kinetic impact of air molecules on the particle. The outgoing energy, Q out, corresponds to thermal radiation emitted from its surface. The difference between them gives us the rate of energy accumulation. This explains why small and fast particles which experience greater drag also accumulate more heat. Once the equations were established, we implement them numerically. Used a fourth-order Runge integrator for a fixed time step to evolve the system in time. On the left, we list the main variables, height, velocity, and accumulated thermal energy. On the right, the key parameters such as gravity, atmospheric scale height, emissivity, and the thresholds for melting and vaporization. At the bottom, we summarize the test conditions and representative trajectories for three cases: intact, melted, and vaporized particles. These plots show how our model behaves from those three representative cases. On the left, height versus time, we see that larger and slower particles fall gradually, while smaller and faster ones slow down and stop earlier, often before reaching the surface. On the right, specific energy versus altitude. This shows how heating grows as the particle enters denser air. Once the energy reaches its threshold, the process stabilizes, intact, melted, or vaporized, depending on the case. Finally, we built a regime map combining many simulations with different initial radius and velocities. Each point represents a possible particle entering the atmosphere. The plot clearly separates three regions: intact grains, melted grains, and vaporized grains. This map summarizes the entire behavior of the model, showing the transition between the different physical outcomes.
For the inverse problem, we assume that we have a distribution of data here on Earth and want to retrieve the distribution of parameters that gave life to this data. Therefore, we assume that these distributions are related to a matrix K, where each component of this matrix comes from integrating the system of differential equations for a given pair of parameters, mainly for a given radius and velocities. But this matrix is not well behaved because we can get the same data we have here on Earth from different data of different pair of parameters in the space of parameters. Therefore, we get, from a probabilistic point of view, the application of a metropolyheuristic algorithm. For this algorithm, we need a likelihood, mainly the distribution of our data given the parameters given a certain set of parameters, and a prior, the prior of our parameters. That is just the probability of getting a certain pair of parameters. We use a Gaussian likelihood and a quadratic prior, and we get that the logarithm of the probability of getting all parameters given all data is proportional to the difference between the observations and the output of the parameters in our model minus a regularization term. To ensure that the distribution we get is as distribution, we use the softmax function. Now we run the metropolyheuristic algorithm. We start from the origin and we get the log posterior of this point, mainly the log posterior of our radius and velocity being 0. Next, we generate a Gaussian distribution with mean our current state and standard deviation, given a standard deviation, and we sample a new state from this new distribution. Now we get the log posterior of this new state, and we get the difference between the log posteriors of our current state and the state we just sampled. We accept the state we just sampled with probability the minimum over 1 and a function that depends on the difference of the log posteriors. That's how we can get from a uniform distribution, mainly our origin, to the distribution that is shown in the slide. We can see that we get a certain level of the velocities, mainly the velocities have marginal with 2 peaks, but one peak of them being 20 kilometers per second, and the radius have only one peak between 100 and 50. How do we know that the metropolyheuristic algorithm have converged? Mathematically, it's certain that it will converge thanks to the properties of the Marcus change that is generated through it, but we can get a look to the residuals to evaluate its convergence. Here we can see that the residuals have a max of 0.04, a total variation of 0.03, and a mean of 0.029, leading us to think that effectively the metropolitan testing algorithm have converged with the given marginal.
Finally, to wrap up, our main takeaway is that the atmosphere is a strong nonlinear filter for cosmic dust. The combination of initial radius and velocity really decides whether a grain reaches the ground intact, RF melt, or gets completely vaporized on the way down. Using the direct model and the pre-computed matrix K, we can go the other way. From an observed surface distribution, we can infer qualitative patterns of the incoming flux, for example, which sizes and speeds are likely over or underrepresented, but always with some uncertainty. The MCMC framework is how we handle that uncertainty. Instead of producing a single best incoming distribution, we get a posterior family of plausible distributions and can see which features, like peaks around certain R0 or B0, are robust and which ones are not. Of course, this comes with limitations. The model is 1D, assumes no fragmentation, a very simple atmosphere, and only a few fixed material parameters, so the results should be read as order of magnitude qualitative insight and not as a final quantitative reconstruction of the real air flux.